Then, welcome to today's webinar. The topic today is form finding and calculation of membrane structures in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal Software company. For instance, the Dlubal website, press releases, the German and English webinars, etc. I will be the moderator today, and my two colleagues can introduce themselves.
Hello, I'm Andreas Niemeyer. I'm responsible by Dlubal for the development of the programs, and especially I take care about the programs for form finding and wind simulations.
Stefan, you are muted.
My name is Stefan Hoffmann and I'm still?
No, it's okay.
Well, I will just shut down my webcam. Yeah, my internet is bad, so sorry. I'm responsible for the customer support and doing some dynamic add-on development, and I will be taking care of the chat.
Okay, thank you. Then we can close our webcams so that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can enter a short question here and we will answer you. If you don't get an answer during the webinar, well, maybe there are too many, then you will get an email after the webinar. The other option is to watch the entire webinar and then email your questions to info@dlubal.com. Then I hand over the screen to Andreas Niemeyer and he can continue.
Okay, thank you, Andreas. Then I take over and start with our webinar about the technical part. Today I want to show you how we can deal with membrane structures in our new generation of M6. For this we planned 4 main points we want to show you. At first, of course, how you can model form-found shapes and work with them in the program. Then how we can organize these shapes to each other with stages. And as third, how we can create wind loads according a CFD analysis on the structure. And finally, how you can design and document such type of structures. Of course, I can't do this completely for one project in 1 hour, but I want to give you an idea how this is working. And you see on the right side some pictures from top to the bottom. So because the new generation have a new input concept for these tools, I want to explain you this on a easy, simple example on a cable at first. Then we go to a, let's say, hypersail surface structure, and afterwards we check or we use all these functions I explained on a more complex structure for such a stadium segment, and finally we take care about wind simulation on the complete stadium model, what you see on the bottom. So don't lose some time and go into the program. I change here to RFEM 6, our new generation program. And for this first part, we define a new model and activate the so-called form finding tools in the add-ons catalog here. And yes, we want to override, and how you can see if you go into the program, it looks generally like the, let's say, past solution, but as you will see, we have some new changes here. So as mentioned, we will explain all new features on a small easy example. I selected here a cable example, therefore let's model it. I use a new member type cable with a cross section, cable cross section. Let's select one from the library, for example, this PE cable with a PE material, cable material with the equivalent stiffness, and define here a cable with the length of 10 meters between 2 points. That the cable will not fly through the air, of course we have to define some boundary conditions, therefore I define here 2 supports. Now, this is the input for the model. As you see, simple cable, and on this structure we explain now all features. And of course what I always do when I explain form finding, I calculate the deflection of this easy example. Therefore, let's calculate the self-weight load case, what is always defined automatically in our program. If we run the analysis of this load case, we will get from the program, as expected, a deflection curve. Here you see 66 millimeters sag. Of course we can deform the sag manually, or let's say scale. We can animate it, and of course when I scale it to 1, you will see that the deflection curve will maybe lie on the topology shape. And this is maybe the first point what I want to mention. Here in our new generation we have programmed an intelligence what draws the topology, so the cable structure in this case, on the deformed shape, in this case with a sag of 66 millimeters. This you can change in the display navigator below the chapter model. Display topology on original shape and deformed shape. The same you can change here with this button, original and deformed shaped. So this is a little change what should help to understand the model a little bit better. So, and then next, go to the next topic. What means of course we calculated now the static analysis with the length of a cable of 10 meters and for the self-weight of the cable itself, which ended up in a 66 millimeter deflection with an internal force maybe here 0.33 kilonewtons. But of course it's a too small cable, moment. Let's make now, because to show you the effects, I expect a bigger force here. Yes, 1.25. But of course, if you see the force here, you could say, I want to simulate here in the program a cable with a longer length, that I can reduce the normal axis force here. And this is possible with our form finding application. And for this, you have to define now, besides the, let's say, self-weight load case, a pre-stress load case. I call it P and define here an action category pre-stress. This is now the step in our form finding tools. And this pre-stress load case is now empty and should be filled with some boundary conditions. And we can fill it with the boundary condition for form finding. We can go to the member loads, to load type form finding, and define here, for example, a geometric definition that we expect for a specific load a sag or a cable length of, let's say, 0.2 meters. And if we apply this load, you will see it looks like a line load or whatever, and it indicates that we get here 0.2 meter sag. And of course everybody could think now, yeah, it's defined now, and if I calculate this load case, we get a sag of 0.2 meters. But we don't get it. We get at least a zero result for forces and a 0 result for deflections. And this is clear because the program can't find a shape for a form finding condition, so for a expected deflection, without knowing in which direction it should run. Should it be downwards, upwards, back, or in front? So it needs a load for which the shape is detected. And in this case, for example, if I take a look on the load case list, we can say, please find me the shape with 20 centimeters for the self-weight, for example. It could be any other load also. But if I say for this load, I have to go to the load combinations and to define it. And for this, I deactivated first the wizard and go to the load combination and say, please combine form finding with self-weight. And this means now for the program, because this combination 1 contains only this form finding pre-stress load case and any other load case, that this is a form finding job for him. And if we run this analysis, the program searches a shape which fits to the conditions. It means he searches a shape where he can fulfill almost this condition 20 centimeters with a corresponding force. Of course, you see here we don't meet the target completely. We have here 213 millimeters and not 200, but this is a cause of accuracy. It's maybe the standard definition for a specific size of model. If you want to have a more certain result, you can change the properties of the calculation. This leads me to the next feature, how this is organized in RFEM 6. Therefore, we changed to the properties, and you saw we calculated CO1, and every load situation, maybe load combinations and load cases, have here a static analysis setting. What means, let's say I can assign to every analysis or load situation a set of calculation parameters. And these calculation parameters have here also a form finding sheet where I can define these settings. You see there are less inputs. We simplified everything a little bit, and I increase now the pre-stress loadings to 50, and after confirmation and rerun we will get the 20 centimeters hopefully, and yes, we get it. So you see the program searched us this shape 20 centimeter with a corresponding force of 0.4 kilonewton. So far this was our first form finding job in RFEM 6. And maybe you saw now that we got, or we gave you as users, a new mighty or power in the program to work with shapes. In difference to our old solution, we can now manage more shapes in one model because I have it now in hand of combination. Before it was only one. And this means now, if you imagine, this is now shape 1, form finding 1 is G plus P, and you say, I want to check in my model also another shape. Maybe the shape should base on a puncture load in the middle. So let's define here a load. For example, I call it N, and give this load case maybe the type permanent. Nope. And define in the middle here, let's say a concentrated load with the size of 10 kilonewton in the middle of the beam and place it here exactly. And now let's create a second parallel shape besides this self-weight based shape. So I go again into this load case and combinations dialog, into load combinations, and create here now a shape maybe F2, based on n plus p. And for this, we only have to change here the input, so p and n in difference to the first one. And if we calculate this, you will see you can do in the same model another shape. What means we have the 200 millimeters in the middle, but if we take a closer look, you see according to this form finding load in the middle, in this concentrated one, we get such a triangle shape with a corresponding force. And you can change in between both shapes. So this is now possible and gives you much more options to check your models or to create something new. So this is one point what I want to show you. So the next point was, and I remember too many questions on the support, how I can deal with partial safety factors in the program. Do you have a solution for it? And with the new generation, we want to give you a solution. So I can say, of course, we can create a third shape. For example, I copy the first one and say, let's scale it up and define here 1.35 as factor, and that we have a clear name 1.35g plus p. And if we calculate this, the program knows I have to do a form finding with the form finding condition of 20 centimeters. It was not scaled up, but with a bigger self-weight load scaled with 1.35, therefore we get a little bigger force on the cable, not 0.4 and 0.56. And you see the program is ready for this. Of course we can also, let's say, scale the pre-stress. What means if I scale the pre-stress 1.35 and only for the name here 1.35 form 4, for example. This was form 3, only that we have a clear description, and calculate, then we can also scale the form finding inputs. You see not 200 and 270. What is the factor 1.35 in between with the corresponding force again. So it's an easy game to work with different shapes in one program now. And this brings me to the next topic. What happens if you want to use these defined shapes for further loadings, maybe surf weight, snow, whatever. And here it's interesting, you have to organize now which shape should be used for which load case. So define at first some additional load. I define here, for example, a variable load with any category. Let's take, for example, this red one. Nope. Now, and apply, for example, 5 kilonewton per meter on the structure here with a projected load. So far we have a load on structure. If I run this load, what happens? Without any further specification, the program applies this load on the 10 meter long cable, yeah? And not in any shape. But if you want to apply it maybe on shape 1, you have to assign it. This means we go again into this dialog, load combinations, and say, please calculate, we give a name, Q on FF1. And this you can do if you define an initial condition or an initial state. So here you specify the shape, for example shape 1. This means we overtake the geometry of mesh and the inner forces, and to get a full set of calculation we apply also the outer loads. form finding loads and the expected, let's say, additional load. And now, according to the situations that we have here defined an initial state as starting shape, the program knows that this is no form finding jobs and only a pure static analysis job. And let's calculate this and take a look how this is looking. And you see, when we take a look on deflection, we have now deflection of 629 millimeters, and this means this starting from the original shape. So this is what we inputted. This is the shape of initial state. This is our form finding shape, and this is deformed shape is the loaded form finding shape. So the program gives you the option to manage all this stuff, and of course not only for one shape, and if you wish you can also apply the same load on shape 2, what means we only change here to shape 2 and exchange here the load to n. And with calculation we get the same task only on, let's say, here original form finding shape 2 plus load is on deformed shape with 493 millimeters with a normal axis force of 177. So this is, let's say, our new philosophy of working with form finding tasks and organizing it in the program. And this brings me to the next point, how we recommend the standard work of using, or the standard use of these tools. And for this, if you may be starting with a new project, of course you don't want to test it like I just showed you. Then on a real project I recommend, and for this we create here a new situation. So I delete all this stuff, go back to load cases, and maybe let's remove this stuff. And now we have this 3 load cases, a standard situation, and in a standard situation I recommend that you use this stuff as with a combination wizard and say please combine me all these load combinations automatically. This means the program overtakes all this stuff, but have to know what is my shape. And if you have to define the program the shape, we create it here as individual load case. So we select both, for example P and G, add it, and say this load case is shape 1. And now we give this shape 1 the pre-stress load case. Now you see we have 2 pre-stresses in it, and we only have to use 1. So I learn my action set, pre-stress, that this is shape, it's not needed, we only want to have a combination with P, and go to the design situations and say our combination wizard, if you combine something, please consider always shape 1 or any other shape. Of course we have to use here Newton-Raphson so far. So now if we go to load combinations, you will see the program combines for us all combinations according rules of standards, so ULS and SLS with factors, without factors, and you see in all combinations automatically the shape 1 is assigned, and even here all load cases, the external loads also placed in the combinations. And with calculate all, you get all forces what are expected in this case. At first he calculates the shapes and then he set it up. So this is maybe the first introduction example what shows you how to work with all these tools in RFEM 6. Of course this is a special example because the shape for cables depends always on the form finding condition, so how big is the sack, for example, plus any load for which we have to detect the shape, the self-weight, for example. But there exist different examples. Maybe the next is here, desktop, a surface structure, a membrane structure. And I prepared this example only to show you it could also work like this. So in this case we have maybe such a sail with typical load cases, surf weight, pre-stress and snow load. So for surf weight, clear the weight coming from the material itself. For pre-stress, we defined here, you see, let's say the inner pre-stress, the membrane tension by a surface load, like we just did it for members with load type form finding and defined here in X and in Y the 3 kilonewton per meter. And you see, if you're running this shape form finding job, you get here the shape of the membrane, you get internal forces in the membrane, what are almost meet the defined 3 kilonewtons. And if you want to combine all these 3 load cases in combinations as standard recommendation, you go into the load case and combination menu, define the combination wizard setting, what is on in default, and learn the, let's say, wizard, please assign always the initial state, the shape from load case 2. Not more. In this case, it's enough. And if we go to load combinations, you see the program assigns us even for this surface structure, this shape from load case 2. And if we run the analysis, the program uses this shape and detects us the forces. As you see, now if we go maybe to the characteristic solution, we have here maybe shape plus surf weight. It's not almost 3 because surf weight is applied afterwards, and if we apply maybe even the snow load, you see the forces are have bigger changes because the load have effect on the given shape. So even this type of model is possible in the new environment. And now we learned that we can use pre-stress load cases with form finding loads to find shapes, to organize shapes, to assign shapes to load situations. I want to go the next step and say it's even possible to use shapes basis on another shapes. And if you have such a task, then you can also use RFEM 6 for it. And I prepared for this type of analysis a special picture to explain it to you, what we want to do. This means you see now here 2 pictures on top, a segment, a ring segment, a 15-degree segment of this stadium below. And if you see this, this consists on a primary and a secondary structure. The primary structure is maybe this column with this bracing in back, with these stay cables and these tension cables with this inner ring. And this is the primary structure. And if this primary structure is set up, the work is coming and hanging in the membrane. And this is the secondary structure. And this demands from you that you have maybe shape 1 for this member structure and shape 2 for this membrane structure. And both could be managed. And this we take a look on now. And we model this part, and afterwards we go into the stadium structure. So let's go back to RFEM. So open a new model. I call it S2. and define all tasks what are needed for modeling this part of Stadium. I go to add-ons and say, please use form finding. And because we have these different stages, so primary and secondary, I activate construction stages and go in. Of course it exists, so overwrite it. And now let's start. So of course it's not easy to model a whole stadium or a fragment from it. So I prepared a DXF background layer. So I go to background layers and import here a layer from a DXF file called base. And you see this is my DXF data. It's on wrong plane, so I rotate it 90 degrees and then by 180, and then everything fits and we can overtake it. And please take care that it's activated, so active, and now we have this, let's say, basic geometry in our program. You see on the bottom there's a tribune only for imagination, and then you see here this main elements is for primary structure, and then the membrane for the secondary structure. At first we model primary, take a look, and then we add the secondary part. So let's start modeling these members. I go to the member dialog, member type beam. Let's select a section. So in my case here, because I don't move the section, my proposals to the final state, but here I would select a diameter of, for example, 1000 millimeters with a thickness of 10, and a material of maybe S200, 355. So let's go to steel according Eurocode. Select here standard according Eurocode, this one, and select the steel here and go. And now we can place this column here in this structure, so from the bottom to the top. And let's add here a bracing member what is connected hinged on the bottom, so if I activate the hinges, and here you have a different cross section, for example 600 millimeter diameter with a thickness of 10. Of course this could be optimized according to the section proof afterwards. So hinges should be hinged on the bottom, so define here hinges about Y and Z, and now we can place here the member between these 2 points. This structure will not be stable, so we have to use now stay cables on it. The stay cables are acting now on the outer fraction of this segment. So at the moment it's only a slice, but it will be a 15-degree segment, so we have to create it. For this we need a center point of our structure, so because I know here the diameter of the structure is 288 meter, I copy this node 144 meter in the middle. And this is now my center for all rotations, and we can create from these nodes now the outer points for this segment. So I select these 3 nodes, rotate it by 7.5 degrees about the global z-axis around this point, and apply, and now minus 15 degree and OK. So now we get these outer nodes. When we take a top view, you see this is maybe the geometry of this 15-degree segment. And now we can place the cables, what means the uninteresting nodes we delete before. Yes, and go to the new member function, use a cable, and now select equivalent sections with an equivalent stiffness. For example, here a solid section with a diameter of 80. So now we can place it here and here, and now to the top. And now we need maybe some suspension cables to the front. Here we have a different diameter, so it's a cable at least. We use here a solid section again with a 30 millimeter diameter, and then we can connect maybe the peak point or top point with the front points, and maybe make some stabilizing cables back to the back bracing. So this is almost the primary structure for the stadium segment. The only thing what is missing is the tension ring around the structure. Let's add it. We take here a cable with a section, and maybe here need some more mass, for example 120 as equivalent section, and connect both points and directly define here a middle point, so divide member for a later connection of the ridge cable. So this is now everything what I have to define for members for the primary state. So I deactivate the DXF, that you see what is left, and now we have to define the, let's say, boundary conditions. And boundary conditions are, let's say, the easiest one are supports. So we define here a fixation, 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 and of course that this front point is not weak. We need a rotational symmetric boundary condition that this is overtaking loads. So I have to simulate this tension ring around. For this I use also nodal supports, but I rotate it in running direction of the cable, what means I fixate the degree of freedom in UY direction with a specific direction around 7.5 degree. Okay. Yes, and now let's copy it that we have it also for the another direction with -7.5. And now we can start applying this support here, and the same, the last for this direction, and we get a structure what can simulate this tension ring. So the structure itself is now ready. The only thing what is missing is the form finding conditions to find the right shape for this structure. And if we want to do something with form finding, we learned already we need a load case pre-stress. So this is G, permanent load case, and here we need a load case P, pre-stress, for defining these form finding conditions. So let's do it like this. This entry is done and define here with member loads, type form finding, geometric definition. So you see we have here different options. So we have geometric definition, we have force condition, but in our case in this type I would say generally he should find a shape with the original length of the cable. So I define geometric length by 100% and apply this on all cables. Okay, so now it's done, and now we should do a combination of both loads because you have to find the shape according to the surf weight, what is clear. We did this before with a load combination, but now we expect that we have a shape on another shape, so we have to organize shapes before, which we can do in the construction stages. In the construction stages we can define now a stage, primary, or not primary, let's say shape 1, it's easier to understand, and we say shape 1 consists on members and nodal supports, and the members I draw a window about everything, okay, and the nodal supports the same. Everything good so far. Okay, so the amount of elements is clarified in this stage, and the only thing what is missing is that the program knows now he should do a form finding for this stage shape 1. What means he should consider these load cases as permanent. And if we calculate this stage with this load selection, it's clear because nothing else is here, he can do a form finding for this type of structure. We get small sacks, we get forces, so everything is clear so far. The next point is to hang in the membrane, what I mentioned before. So if we take a look on background layer and set it here, you see now we have to bring in the membrane on the already deflected and loaded shape 1. To do this, I, let's say, delete mesh and start modeling the rest. That means we define, for example, the boundaries of the membrane. It's maybe here, it's running to this point, and even from here to the top. The only problem is now that I have to specify that the cable is not running in the other one, so I rotate now my, let's say, grid point plane and use some arc lines to cover this. This I simplify right now for this presentation and pick here the line, the same for this here. Of course, it's not important if this line will match the DXF shape, because the form finding application itself will find the right place of structure. So it's not a target, it's only a, let's say, a tendence where it should go. And now we can, let's say, not completely, we need here a splice cable, so also define here a splice, and if we want to define it here on the perpendicular point, so we can do like this. Now we can deactivate this shape. You see we specified the boundaries for the membrane and can support now cables on these boundaries. So I select all these lines, go into the library, edit lines, and say these lines should hold some members with the type cable, and now define the last section, for example, one with 20 millimeters. So far it's good, and now we can maybe bring in some membranes in this cable boundaries. So because this produces some not plane surfaces, I select as initial shape a quadrangular surface with the type membrane, and go to the library. And this is maybe new. In the library we defined now even fabric material, standard materials with an average set of values of stiffness. And for example, we use here the glass PTFE type 3 option. The program knows according to defined stiffnesses even the reference thickness of 1 millimeter here, and now we can place these surfaces in between these cable boundaries. So if we take a look on maybe transparent view, you see the definition is now made, and now we only have to mirror this stuff on the another side. So use the mirror function, create a copy about XZ plane in the middle, and go. So all this is done, and now to finalize all this stuff, we have to take care again about boundaries. One type of boundary is clear. We have to fixate these lower corners here, and we have still to check that, let's say, the rotational symmetric support is working for this 15-degree segment. This means we have to support these boundary lines. So we use here line support on a local axis in local y direction, and pick these lines here. So far this is done. This is so, let's say, a fat green line. I don't like it to see it all the time, therefore I deactivate it here with type for lines in Display Navigator. And now the last point is to specify even form finding topics. So we want to pre-stress the membrane with a, let's say, tension load. So let's go to surface load, type form finding, and we can define here the method of application, standard or projection, force or stress, and we say, for example, we have here 2 kilonewton in X and in Y direction, and draw it above the model. So this is done, and now only the last final boundary cables are missing, and now I see so many loads and I lost my overview. If you have also the same situation, please go to visibilities, generated members by section, and activate the last one, and you see these members are left, and we can go to member load, form finding, and can select the definition. So geometric you already saw, but we have also force options, and here you get also some more options for shapes. In RFEM 6 you have now the option to place an average force, maximum force, minimum force on member, horizontal tension component, a tension at start, at end, a minimum tension at start and end, force density. So there are more options like in the old program. We use now average force with, for example, 50 kilonewtons, and draw this stuff over the structure, and you see the loads are set. So now loads are defined, boundaries are defined. The only thing what is missing now is that the program don't know what is my secondary state. So let's specify it in the stages and say here, please create a new stage, and we call it shape 2 on shape 1. Yeah? And for this we say, okay, please consider also surfaces, please consider also line supports, and because we know no more elements will come, we say all, and all. So elements are clear. So here we know which elements should be considered, and in the loads the program knows it automatically because stage 1 consists on self weight and pre-stress, so it's a form finding topic because it's permanent. The same is acting for the second because it's permanent. So if we calculate now stage 2, the program have to detect at first stage 1 because it's a basis, and now if he have stage 1 he calculates stage 2. So we have a sequence of shapes. What is quite cool function, I would say, and gives us really more a big potential to calculate a lot of structures. And you see now we have in our structure, now when the update is ready, now the shape of the membrane on the already defined shape 1 with a new set of forces. Of course you see here maybe even the forces in membrane, forces in cables, and it's clear you can change back even to stage 1 what holds only, let's say, the member structures, and you get only forces on these elements and not more. So there is a pure organization of, let's say, which element should be considered and which load should be considered, and RFEM 6 have it open for you, is open for your definition. And now if we have let's say a sequence of shapes, the question will come up, now will I apply my additional loads? Is there not a weird situation or a chaos? No, it isn't. So let's create maybe a live load or whatever, and define here in the load list, for example, a Q load, where we say maybe here this red one, and we apply on the surfaces. So a surface load force in projected area maybe 0.2 kilonewtons. And we draw it over the structure, and you see it plays the load above. The only question is now, at which stage should this load be used? And clear, we have to go back in the load combination menu to the stages and say, oh no, we have to do something at first. We have to give the program information what is now the basis for your further calculation. And for this we have to create a last final stage, and we call it structural calculation. Calculation on shape 2. And for this we can now start assigning loads. What means you see shape 1 have a start condition, shape 2 basis on shape 1, and shape 3 or stage 3 basis on shape 2. And here we can say, please consider the load case 3 variable non-permanent in your stage. And now let's say everything is done for calculation, and let's pick in load combination top. And what happens, the program prepares us let's say load combinations for ultimate limit state and for serviceability. But if you take a closer look, oh, initial conditions, initial states are not defined. So this is not so good. But it's the same like for load cases. The program have to know for which stage. So let's go back and say, of course we want to have, let's say, combinations for all stages. And the wizard have to say, yes, I do it for stages only with Newton-Raphson solver. And if we go back to load combinations, you see the list is a little bit longer, but have now a stages allocation. Stage 1, stage 2, stage 3. Here we have 2 combinations, the same for the characteristic ones. And as you see, we have now here even defined stage 2 as basis and working on the element set of stage 3. So even this setting is pre-filled with all load cases. Now we can start calculating all. Before I would say let's deactivate here these load cases that we don't have to wait for all, and calculate here maybe simplified a little bit. No, we can calculate all. Okay. So now the program calculating all stages at the time, let's say, how to say, not to say it wrong. The program calculate always the load combinations for the stages what are already calculated. So he can't calculate maybe the final combination which bases on a state what is not prepared so far. So now we have to wait to get the analysis of these 14 load situations based on different statistical systems. As you see, there are always running on my computer 4 processes at the same time. This is connected to a solver manager because the program have intelligence which searches how many processors are available and shares all this calculation task to these processors to get results back, and uses so the complete available hardware what is possible. Of course, he cannot overjump stages in this case. So what you also can see you can select here even every process manually. Maybe combination 1 have here a pretty small deflection, combination 2 have a bigger one because the membrane is moving from its origin place to the uplifted place, which is a longer way from in space to go. So now results are ready. You see maybe nothing according to so many loads, but what is clear, you see here, for example, let's open maybe combination 3, what is here surf weight and pre-stress in these different shapes. So this is maybe a little bit scaled, but now even you can select the different stages with the different situations. No? And this brings us to the state how I can do maybe or check if now membrane and members so far okay. And for this you can activate in the calculation add-ons here the option, for example, stress strain analysis, and with activation of the stress strain analysis you get here in your table or option stress strain where you can say what should be calculated. And for example, for members we say please check for us, for example, you can select between all these stress components. It's endless and I think also boring. So from my point of view, sigma equivalent is enough, and check it against limit equivalent stress and apply. For surfaces you also have the same option. Here you can say equivalent stress is not so good here, but you can say please check sigma x and y with a user-defined stress, for example 35, and here also use for example 25. So it depends on you what the limit stress is. And now if you run it, you get here maybe a utilization check for all these elements according to stresses what are coming from all these stages. So now we get a result. Of course now the nice shape of the form found shape disappears because this is valid for all load combinations from different stages, so the program draws the shape on the original shape. But this is one point. Now you see we get results for members and for surfaces. So let's deactivate it first for surfaces and deactivate it here, for example, stress ratios, hide the mesh, make maybe a wireframe model, and you see okay, almost all cables fits, the rest we have to rework. So here we have some red ones, so you need a bigger cross section. So this could be visualized, and you get also a result table on it, stresses on member by stages, by design situation, or by section, where you get the table. This one is maybe the limit state for the different cross section, for example. No? The same for, let's say, surfaces. Here we have also utilization, and you see maybe stresses on surfaces. So far the grid points are fine. Stresses by material, by thickness, by surface. You get always a table where the existing with the limit is compared and get a check or not. So far. Now you see this is the way of design, and if you have to bring all this calculation on a paper, we offer now program a printed report. This printed report could be opened here, and of course at first you have to give a scope what should be everything inside. Take a look, you get maybe all options, maybe basic objects, node, materials. All these topics could be bring in shape of a table, even stress analysis, what we activated. And here you can say, error warnings are not interesting for surfaces. I want to document maybe table surface by surface number, and save and show me these tables. Now the program creates a report where we maybe get a sum up of all input data according to the scope what we just defined. It's a styled document where you see with a cover, with a content list, and also all data like sections, members are visualized with nice small pictures, explaining pictures that the reader of the document understand what is going on. You can zoom it if it's needed, and of course the results what we just looked on are defined. So here's our list for cross sections for surfaces. So even this list what we see in main program could be visualized in this document, and if you are forced to make it more reader friendly, you can add also some pictures. So jump back. So the program, the menu is parallel opened, and you can say, please print me a picture of the member utilizations into the document, print that report, and say here, please make me a window filling picture with a height of 50% of page high, and yeah, okay, and make me a utilization picture of the surface utilization from top view with values on surfaces with maybe extreme values. So everything is possible. You can create your own pictures what expected, and let's go to print and move it into reports. The same for the Y direction, and print, and if it fits we update the report. So now the program is updated. You see the pictures are inserted in time, and the process is still running, and we can work with this document, and when it's updated it maybe it's regenerated and you have all these pictures inside. So this is not a big deal, and to bring in some result pictures. And what is not nice here, if the maybe color scale is inside the picture and it's is not so good, so you can go to properties and can say please print color scale outside graphics, and the program is updating the pictures where the scale is outside. So to round it up, finally you could be forced to make some description of your structure, and you have, if you have some prepared PDFs or whatever, you can read it in. So go to insert PDF, go to, maybe I have here my folder for webinar. I have maybe a PDF of the website from Antonio Farrer about this stadion in Riyadh. We can bring it in by one click, and you have it here imported. It's not a bottleneck regarding performance, so you can also still work with this report and jump to different positions and create a final documentation for your clients. So maybe this was one workflow how to work with the program to create maybe shapes based on another shapes. And now maybe we can think about how to finalize all this analysis, and for this is maybe a look into the low case list important, because we did now only maybe basic checks on this small 15-degree check, but to do a full analysis you also have to consider wind loads. And wind loads is now, let's say, for this type of structure not so easy, because we have no concept how the load distribution is looking like, and therefore a question come up how we can how big the loads from wind are, and maybe You can solve it by a real wind tunnel test, or what we can offer, you can place your structure in a numerical wind tunnel. And for this, you need a full model, not only a 50-degree segment. Therefore, you can say, please take this structure and rotate it maybe here by 15 degree around the center with 23 steps, and confirm this setting. And you will see that it's not a big deal to create such a big stadium model now, because if you have your system of your structure and you modeled quite clear, it's no big deal to bring in or to combine it as a bigger model. Even the stages topic, all this is not so critical. And now if you have such a model, you can place it completely in a numerical wind tunnel. And because this takes some calculation time, I prepared here a model for you. So I jump now, let's say, in another RFEM and move it here on this side. So this is the same, almost the same structure, even with these stages what we just discussed. The only difference is, the main difference is that I created here a wind load case. And this wind load case, like you see in analysis type, have a different flag. And this different flag coming because in add-ons is also activated the wind simulation. And if you activated the wind simulation, you get the option that you can define here in analysis type wind simulation. This opens for you two new registers here, and you can say, please use this model with maybe this stage and this shape for a wind simulation in a numerical wind tunnel, where the wind medium is according this density, kinematic viscosity, this turbulence model and meshing, with maybe this wind profile, what could be defined, user-defined in a table or according any standards. And the wind is coming from this angular direction. So here you specify maybe the medium around the model, the input wind speed, and the size of wind tunnel with the input wind speed. And if you calculate this load case, this is a two-step process, what means the program is moving the model in background into a numerical wind tunnel according all defined settings, calculating the wind medium around the model. Let's take a look. You see, calculating here, maybe this is the numerical wind tunnel structure. You see wind tunnel with input window, and now the program or this process detecting maybe the pressure around the structure. Now this is only maybe a slice of it, but you can see how the pressure is changing. You can also say, please show me results in this slice. It calculates the wind velocity around the structure and even the wind's direction. Yeah. So, and with this information, the wind flow for the structure could be, let's say, detected. And according to this information, the program can, let's say, calculate the pressure on the structure. You see, if it's updated, that we have here in front, of course, some pressure, here some suction or below how to see even in the back section. So all this influence is given then, and these forces, these pressures are given back to RFEM, to this load case with wind analysis, and could be used or are used for a subsequent static analysis. And this is a two-step calculation what I just mentioned, and leads to the situation that you can, it's running, can detect for these forces, new internal forces in this structure. Now it's ready, and you see if I activate, let's say, the loads, you see this is maybe the wind tunnel. If we show everything, you see this is the input wind speed like we just saw for 0 degree in X. And now if I activate forces, you see also this is now the structure answer of the wind simulation with the loads what wind simulation calculated on the structure. Here we have, for example, the internal forces, normal axis forces. Maybe only I rotated that we have now, yeah, exactly. And even we get deflections on the structure. All this, let's say, feedback of the structure is now given according to these loads, and now with this information and this real load distribution of wind load, you can go ahead like I just showed you before. You can start combination of these loads, calculate maybe loads for ultimate limit state and serviceability state, and feed it into this design add-ons, for example stress strain or steel design, as you have to do according to the rules of the buildings. And this brings me now to the end of my webinar, and I give back to Andreas.
Okay, thank you, Andreas, for this nice presentation. I hold back the screen. Because I would like to give you an additional information, a general information. In RFEM 6 and R/9 we have new the Dlubal Center. You can open this with this button. I open it and bring it here on the screen. Okay, and then you have here my account, and you can find, yeah, a lot of information here. For example, my messages. We have to wait some time. Okay, here new version, recorded webinars, etc. Then your personal data, the company data, the users, quotes, invoices, etc. Licenses, products to download. The newest version can you find here. That's the new generation of M6, R/9. And that's the old generation. And then quite important, the development. You can see implemented features here, open features and single programs. You can submit bugs. You can submit your request of a new feature, and we decide if it will be implemented and so on. And you can find this or can reach this account also from the website. Here under my account you can log in here, and if you haven't any account, you can create a new account. It's for free. Those are free information for you. Another tip is you can find it under education and e-learning. Sorry, education, e-learning, and then RFEM 6 for beginners. If you want to start with RFEM 6, or you can recommend it to your colleagues, that's a tutorial with 20 videos, and that would be a good start in the new program generation. Okay, then last information. Some of you asked if the webinar will be recorded. Yes, you will get an email in some days, and on our website under news and events you can find it as well. Under webinars you can find today's webinar here. You will get an email with a direct link to that page, and then the next days you will find the recording here, the presentation slides with additional information about our free tools, for example, the FAQ, the knowledge database, and so on. And then here are the 2 models to download. Okay, that brings me to the end. I say thank you for your attention. Thanks to my colleagues. Thanks to Andreas for the nice presentation. Thanks to Stefan for answering the questions. I wish all a nice rest of the day. Stay healthy. Bye-bye.